Hello, I'm Aishara Mahajan, and in this video I will provide an overview of my dissertation project on developing a web-based visualization tool to aid decision-making for architects, designers, and urban planners. This tool enables the comparison and evaluation of different design variations and their data through an accessible and user-friendly interface. The built environment is becoming increasingly complex with the need to optimize for factors like sustainability, energy efficiency, occupant well-being, and more. This creates vast amount of data that professionals must analyze to make informed design choices. In architecture and urban planning today, professionals are increasingly utilizing data-driven analysis to take informed design decisions and create optimal and sustainable structures. However, comprehensively evaluating multiple design options at early stages and their complex data remains a key challenge. Conventional manual methods for design comparison are often cumbersome, while existing tools lack accessibility or user-friendliness. My research aims to address this gap by creating an intuitive web-based tool for architects and planners to visually explore design variations and their impacts, enabling data-driven decision-making by giving visual representations of the data generated through analysis softwares like Ladybug in Grasshopper. To achieve the research aim, literature study is focused on need of visual analysis tools to facilitate a better decision-making process in the early stages of design and defining the research gap. My literature review began by analyzing research on data visualization techniques for building analysis with a focus on solar and daylight modeling. This area of research revealed the need for more effective and intuitive visualization methods to understand complex building performance data that was being generated by the user on various softwares, one of which is the Ladybug tool, which led me to the niche of selection for this project, which is daylight analysis. Additional literature analyzed include web-based visualization tools used in architectural education. These demonstrate the benefits of web-based visualization tools for improving students' understanding of structural and technical concepts. Finally, the literature review explored was for computational urban planning tools and their capabilities for design optimization and analysis. However, these tools often lack cohesive workflows connecting urban analytics to design outcomes. In summary, the literature review revealed a substantive gap in accessible comparative analysis and decision-making tools tailored to the needs of architects and urban planners. My research aims to directly address this gap through the development of a purpose-built web-based visualization tool. The literature review also served as a collection of case studies aimed to identify algorithms and patterns for generating visual representations of 3D data. In this project, to achieve the objectives effectively, the methodology can be broadly divided into several key stages. Through this process, a strong emphasis on testing and validation to ensure the accuracy and reliability of the visual representations were maintained. Finally, various frameworks and libraries based on the research were used to create an interactive and user-friendly web-based tool. The methodology embodies a balance between theoretical insights and practical implementation, enabling me to deliver a solution. While Ladybug provides powerful analyzing capabilities, this tool acts as a bridge to integrate that data into broader design or decision-making processes. For example, users can visualize how daylight levels affect designs and then export or share those visualizations. For the purpose of this project, a niche of daylighting analysis for parametric facade design is chosen. The tool analyzes and filters data to the user's relevant data requirement in a more interactive, understandable, and graphical manner. Along with the datasets, the tool also allows the users to upload their models in OBJ file format to the viewers to visualize their analysis in a visual way. This tool is a dedicated interface for visualizing the daylight and illumination data generated by Ladybug in Grasshopper. The Ladybug tool generates the data for annual daylight analysis in a particular format. With the annual daylight analysis results exported, it gives the illumination value for each sensor on the plane specified by the user in lux, which is the SI unit for illuminance. Once the dataset is generated, it can be uploaded in the tool. The tool is hosted on the Django server and is designed using HTML and CSS. Once the dataset is loaded, the algorithm for this tool identifies the patterns of this result datasets and filters the data as required to generate the graphs. These datasets, which are .csv files, are parsed using the papaparse library in JavaScript. This becomes necessary as the exported dataset is in a particular format that needs to be organized in a format that is acceptable by the library to plot the graphs. The results of the annual daylight analysis component by Ladybug can be visualized in Grasshopper in percentage values. However, a lot of functionality is needed to view and filter the data as per the user's requirement. The user needs to run a simulation each time the date, month, and time of the day are changed. This data can then be imported in the tool for the user to easily filter it and view the simulation result without actually having to run the simulation multiple times. The selected date is passed to a date variable in the code that formats the date according to the date format in the dataset exported by Ladybug tool. The data is then filtered based on the date variable. Once the date and times are selected, the tool filters the data into categories. The first data, which is filtered on the basis of the date selected, each data set has 24, which is one for each hour of the day, rows of the selected date. The second set of data, which is based on the selected date as well as the selected time. Once the data is filtered, two graphs are generated. After considering and evaluating various types of data visualizations, two types of graphs were selected which can aid a better understanding. The first graph, which is a line scatter graph, shows the total illuminance of the room over time throughout the day of the selected date. The second graph, which is a scattered graph, shows the illumination values for the selected date and time for each sensor on the plane which was set in Grasshopper. Both these graphs are interactive and the results can be exported and downloaded as an image. This facilitates the user to be able to share their analysis. Graphs for all the data sets are imposed and layered on each other for an effective comparative analysis. The user can create a plane which is the same dimensions as the model in Grasshopper by inputting length and width values. The plane is divided in a grid based on the number of sensors detected in the dataset. In order to create this interactive visualization of the simulation, the study then delved into understanding the sequence by which Ladybug tool generates grid points, with a specific focus on replicating and accurately positioning that sensors on the generated plane. This process was closely examined and analyzed to ensure precision and reliability in sensor placement. Once the sensors were placed accurately, a heat map of illumination values was placed on the grid with the illumination values specified in the dataset. The user can view these in the interactive viewers, which allow the users to view a side-by-side comparison for each design variation. The user can also upload an object file of the facade for which the daylight analysis was simulated for a better understanding of the result. As a result, this tool empowers users to make decisions that have an impact on their project outcomes in early stages of design. To achieve this, the tool uses the 3JS cross-browser library for JavaScript, which is one of the most powerful libraries to create and display animated 3D computer graphics in a web browser. The deliberate and strategic design of the tool includes 3 viewers, providing users with an advantage in design analysis and evaluation. By having multiple viewers, professionals can easily compare design variations side by side. This increases the user experience and simplifies the process of identifying the optimal design solution. In conclusion, this web-based visualization tool has the potential to be a valuable addition to the existing computational tools for architects, designers, and urban planners, aligning with the aim and objective of the study. This tool is adaptive and has the capability to contribute in the field of generative and predictive planning and analyzing tools that enable users to take informed decisions. Such tools can not only be useful to the users, but also can bridge the gap between technical complexity and ease of use, catering to users with all levels of expertise. The tool's visualization techniques, with the help of computer analysis, offers user a visually comprehensible means of exploring complex design analysis. Moreover, its ability to assess the impact of design variations is a significant step towards sustainable and efficient design solutions and taking informed and data-driven decisions towards the optimal design. As we look to the future of architecture and urban planning, the proposed solution empowers professionals to make choices that contribute to more sustainable, environmentally responsible, and aesthetically pleasing built environment. It presents a vital resource in the quest for smarter, more informed, and ecological conscious design practices. The future scope for this tool is promising, with several additions that can be made for further enhancements and integration into evolving field of generative planning, tools, and sustainable design. Some potential directions for future development include advanced simulation capabilities, which is enhancing the tool's simulation capabilities by incorporating a real-time weather data and dynamic environmental factors. This would enable the users to perform more accurate and dynamic daylight simulations considering the changing weather conditions. Machine learning integration. Integrating machine learning algorithms for predictive analysis. This could enable the tool to suggest design variations based on historical data and user preferences, further streamlining the decision-making process. Collaborative features. Adding collaborative features that enable multiple users to work on design simulations that will allow the users for interdisciplinary collaborations among architects, designers, engineers, and environmental consultants. Integrating with building information modeling. Integrating with BIM software to provide a comprehensive platform for architects and designers to analyze and visualize daylight alongside with other building parameters such as structural integrity and energy efficiency. Energy analysis. Expanding the tool's capability to perform energy analysis in conjunction with daylight analysis, allowing users to optimize designs not only for natural light but also for energy efficiency. Cloud-based collaboration. Implementing cloud-based collaboration features to facilitate easy sharing of designs and analysis results among project teams regardless of their physical location. In summary, the future scope for this tool is to evolve into a comprehensive platform that not only simplifies daylight analysis but also integrates seamlessly with other aspects of building design and construction, while continuously embracing technological advancements to stay at the forefront of sustainable design tools.